Well, hello friends. Welcome back to Commute Talk. Today it is a bit rainy and a bit cold, so jacket season has officially started. And I thought I would talk a little bit about multitasking in Serenity and how that's implemented. So basically, the main building block in Serenity is the thread in the kernel. There's a thread object, and every process has at least one thread. When you create a new process, it has one thread, the main thread, and then you can create more threads if you like. The kernel is also able to spawn threads of its own that run in a privileged mode where it can access kernel data structures and stuff like that. But the majority of threads are user space threads, and most of them are main threads because most processes are not multi-threaded. But anyway, the threads are identified by a thread ID and a process ID. So the same thread ID exists in multiple processes. Like the main thread is always number 0, for instance. So you'll have thread ID 0 in many different process IDs. And so implementation-wise, since we're only supporting the x86 CPU at the moment, it's kind of specific to that. So each thread has a task segment, like a TSS, if you're familiar, and each thread has an entry in the global descriptor table of the CPU. So we're using mostly hardware task switching at the moment, but we're kind of limited by that because we'll run out of GDT entries eventually. I think you can only have 256 entries, and then one of them has to be a null selector, so we're going to run out of those if we want to have more processes than 250. But it hasn't been an issue yet, but eventually I'll have to do something about that. But basically, the multitasking in the kernel is done by the scheduler class, and the scheduler's job is to figure out which thread to run next. And the scheduler itself will run, I think we have a timer that wakes it up 1,000 times per second, so the timer runs at 1,000 hertz, and that's also the timer that counts the system time, and it has a few other jobs, but we will wake up the scheduler 1,000 times per second, and then we will decrement the currently running thread's time slice and see if it's time to pick someone else to run. So I guess I should say that the scheduler is a very simple round-robin scheduler with block states and time slice, priority-specific time slices, and some lock smarts. But it is a very naive scheduler still because I haven't put that much time on scheduling yet. So basically, when the thread is chosen to run, then we'll give him a time slice, which might be, it's dependent on the thread priority. So if you're a normal priority thread, then you might get something like 5 time slices, which means that you're going to run for 5 milliseconds, which is a pretty long time, but very often threads finish a lot faster than that, and they give back control to the scheduler. But so we wake up 1,000 times per second, we decrement the current time slice and check if it's time to switch to someone else. If it is, then we go in this scheduler function called pick next, which is where we pick the next thread that's going to run. And in there we look at, so we have 2 lists of threads at the moment. We have all the non-runnable threads and the runnable threads. And when we get to pick next, then the first thing we do is that we look over all the threads that are not runnable, and we check if something changed that would make them now runnable. And that's implemented via this nice mechanism called the thread blocker. So when a thread becomes non-runnable, it's because it's blocked for some reason, and then we have this object that's called a thread blocker, which is instantiated on the stack in the thread in order to block itself. And the scheduler finds a pointer to the thread blocker for each thread, and then asks the blocker object, is it okay if I unblock you now? And that's how unblocking works at the moment. And it's really very handy when you're working with it, because you can implement like arbitrary conditions for blocking by just making a custom thread blocker. Anyways, so that's the first thing that we do. And then we look at signals. So if there are threads that have pending signals, then the scheduler will go in for each of those threads and mess up their state so that the next time they try to run, they will be in the signal handler instead, if appropriate, or maybe they would exit or whatever. But it will take care of dispatching the signals in case there are any pending signals anywhere. So that's the second thing that it does. And of course, if you're dispatching a signal to a thread that was previously blocked, that might mean that that thread has now become runnable. So it's like the second half of the unblocking phase, really, is checking if we should dispatch some signals, since that may unblock threads. And then when we've done this, then now we have a list of runnable threads, probably. So what we do is we just take the currently running one, put him at the end of that list, and then we just pick the next one, and we switch over to that thread. And I mean, doing the context switch is basically like a whole bunch of x86 stuff where we just set everything up so that we can, when we return from the timer interrupt that got us here, then we can actually return to the new thread instead of returning to wherever we interrupted. And yeah, that's essentially the scheduler, how it works. So it is very, very simple. And like I was saying, the two smart things that it does have is the time slices are scaled based on process priority. So a higher priority process will have larger time slices, which means that he gets to run for a little longer before we interrupt him to run someone else. But obviously that's not a perfect priority system. We should probably also be servicing those threads more often, but we currently don't. That's, to be implemented, as so many things are in this system. And then another thing that we do is we have some lock smarts, and this is in the kernel only, really, but in the kernel there are various locks, and the scheduler knows, or it's not the scheduler who knows, but in the code that locks, then, in the locking code itself, we will figure out if someone else is holding a lock that we're interested in, we will give the remainder of our time slice to that thread so that it has a chance to finish sooner, because we can't do anything anyway until the lock becomes available. So it's called donation in the kernel, and actually it's exposed to user space as well. So it's possible to do this from user space. You can say like, hey, my time slice, just donate it to this other thread. And you can only donate to threads within your own process. So it's a cute little mechanism. I like it. But yeah, those are really the only two smart things in the scheduler. The rest of it is round robin, very, very simple. And that's basically how multitasking is implemented. Now, when it comes to system calls, Um, we currently can't handle two threads in the same process being in the kernel doing system call stuff at the same time. So what we do there is we just have a big lock. So every process has a big lock. It's called the big lock. And when a thread enters syscall, then before it proceeds with actually doing the kernel things, it will acquire the big lock for the process. And so that ensures that no two threads, only one thread can be in the kernel at the same time in the same process. And there's a little bit of finessing with that. If we do a syscall that has to block, then when a thread blocks, then it will release the big lock before blocking, and then when it unblocks, then it will retake the big lock. So if you're reading this code, you might come across that, and it looks a little bit hairy, but it's pretty simple, really. But yeah, that's the big lock in the process. And I guess the one thing I didn't mention is that there is a yielding mechanism, and that's how processes are able, or threads are able to stop running before their time slice runs out. So what you do then is you make a syscall, you call sched yield, or if you're in the kernel, you just call the yield function in the scheduler class. It's a static function. And what happens then is that you're basically telling the scheduler, I got nothing else to do, so please take control away from me and give it to someone else. And the scheduler will do exactly that, and just switch to some other process that's waiting to, or some other thread that's waiting to run. And yeah, that's yielding. And whenever you block, block implies yield, right? So after a thread blocks for any reason, then it will immediately yield automatically, so that someone else can run, because obviously once you're blocked, you're useless until you unblock. Yeah. Oh yeah, right. And there's also the idle thread, also known as the kernel thread, which is a thread that does one thing. It halts the CPU in a loop, basically. And if there are no runnable threads, when the scheduler tries to pick the next thread to run, then it will automatically fall back to the kernel thread, which means idle. So it will just schedule that to run, and then it will halt the CPU, and then we will wait for the timer interrupt to wake it up again. Now there's a little mechanism there also, that if we get any other IRQ when we're idle, then the next time we get to the kernel thread, to the idle loop, then we will immediately yield instead of halting once more. Because we used to have this issue that you would get an IRQ, say from the network card, and we would put some packet into a read buffer, and then now the network task could run, right, and react to this incoming data, but we had otherwise been idle. So what the scheduler would do is that it would schedule because you got the IRQ from the network card, but then you would go back to what you were doing, which might have been the idle thread doing nothing. So it would halt again and wait for the timer interrupt to wake up and finally discover that maybe we should do something about that network packet. So there is a mechanism around that where if we get interrupted in the kernel thread, or in the idle thread, maybe I should call it the idle thread, then we will check if we got some IRQ that we should wake up from immediately, instead of just going back to sleep, basically. So that's basically the whole thing, I think. So I hope I managed to get everything in there. If you have questions, feel free to ask, but I encourage you to look at the code if you're interested in this, because it is really, really very simple. And if you ever wanted to play around with an actually working scheduler that's not at all difficult to comprehend, then Serenity has just that. It is not too complicated. You can definitely get your head around it. And I encourage everyone to play with it if you're interested. And if you make something better or fix some bug, then let me know, because I would be very happy about that. But yeah, so I'm what is this, day 3 or something of taking a break from programming, and I'm starting to feel like maybe I should get back to programming. So let's see how long I can take this. But anyways, I hope you're having a good day, and thank you for hanging out with me on the commute. I'll see you next time. Bye.